So first time the game was run, there was a minor problem, which was that one team didn't buy enough raw materials for the finished goods they produced, which resulted in a negative inventory, which is not possible. So we had to rerun the game. But we didn't find this out until I'd already prepared these results. So these results are, I checked the new results compared to the old results, and they were very, very, very close. So these numbers are off a teensy bit from what they actually are, but they're very, very little difference at all. Okay, here is the standings as of period 4. Couple of things. So look, Rack at It has been consistently in first place the whole time. Tiger LLC continues its run up the ladder all the way into second place. And similarly, Spice Rack has made a big jump up as well. On the other hand, 30 Rack took a big drop. And Won't Rack Down also took a big drop. And then we have our consistent groups like IRAC and Rack and Roll and CD's Racks, who don't seem to be able to quite drag themselves out of the basement. This is the price, the plot of sales versus price for this period. And if we compare it to other periods, so the most recent period is the blue circles. So it looks like still fairly consistent. It looks like people were, I don't know. Looks like demand is a little lower than in previous periods. And this is this period's plot, separated by different teams. So you see there were two teams over here, Won't Rack Down and Racketeers, who set some fairly low prices. There were a couple of teams who set some high prices. There were a bunch of prices that were like 75 or higher that got 0 sales. But most everybody is right here in the middle. And so that's that for sales versus price. Here are total assets. Again, you can kind of see, if you look at how far apart these points are, look, Rack at It has a good lead. There's a group of, it looks like 5 other teams that are very close. And then the other half. Here's stock price. Look, Rack at It obviously is kind of ahead in all aspects of the game. The one kind of strange one is CD's Racks. They're not doing very well in terms of assets, but their stock price remains fairly high, although it took a significant dip in the last period. So here's the industry report. Here are the negative inventory I mentioned. That has now been corrected. We do see that most companies do have finished goods inventories. There are 3 that have none, and 1 that has a fairly large number. We see stock prices as high as $2.71. I must have missed, look, Rack at It. Nope. What am I doing? I'm sorry, I did earnings per share. Stock price, look, Rack at It should have the highest. Come on. At $23. And the lowest is probably Rack City, $18.20. And earnings per share, got some good earnings per share over $2, and then negative for 30 racks. That was a problem for them. We have some fairly large dividends being declared by different companies. And we have a few insider trades. These are companies that are all buying themselves. And then the sales for the last period. 30 rack had very low sales. That probably accounts for what happened to them this period. Rack and Roll had very large sales. Oops, sorry about that. And a couple other companies had reasonably large sales too, although I think they had open plants, so those were probably pretty good. So I'm thinking if I look at finished goods inventories, most companies are sitting on finished goods inventories, some with a fairly large number. And I think that's probably because plants opened and people did not sell everything that they made. Does anybody have any questions about the game? Okay, I see the message from Sarah. Thank you. Any questions about the game? Yeah, so please make sure that you buy enough raw materials to produce what you're going to make in the future. That would be helpful. All right, I don't see any questions. Okay, so today we're talking about basically production planning. And along the way, we're going to talk a little bit about MRP and lot sizing. And then sort of the main analytical tool we're learning this time is what's called dynamic programming. We use that to solve some of these problems. Production planning, the general idea is how much to make and when to make it. And I'm going to start with a little history lesson. No, I'm not. Introduction. So we've seen EOQ models in the past, which is kind of how much to order, which is kind of the same as how much to make. We're going to talk here about MRP. MRP assumes demand is known. It's a multi-period problem, and it assumes that demand fluctuates from period to period. And basically, it deals with making something that has many components and assemblies and sub-assemblies, and it tries to schedule the production of those things. MRP, I say MRP is, gosh darn it, I say MRP is very old, but I remember when it was invented, so I guess you could still say it's very old. It had a couple of interesting things about it. It was sort of the first time people started thinking about supply chains. It was one of the very early uses of computers in production, manufacturing, and running a business. And these MRP systems are what have evolved into what are now called ERP systems, Enterprise Resource Planning Systems, which are a very big deal now. Most companies have them. The industry leader is SAP, who you may have heard of. They're a huge conglomerate. And so this all came from these very simple MRP systems. Okay, so production plan basically specifies how much of each item to make in each time period, when to make them, how much to make, what's the lot size you're going to make, and then a final schedule for production. An MRP, basically it takes a master production schedule think of this as a schedule for finished goods, and it takes a materials requirement plan that kind of explodes. it's like a bill of materials, sort of. It explodes out all of the assemblies and sub-assemblies. And then it provides a detailed shop schedule for all of the sub-assemblies, parts, and the like as well. Okay, so let's just look through an example, because it's really a very simple idea. But imagine that you have your finished goods are a computer, and it consists of two components. We're worried about disk drives and a motherboard, and then the motherboard consists of some other boards and some DRAM chips. So for each of these sub-assemblies, if you will, we have a lead time. So that's how far in advance you have to order them. So if you order them now, they'll be done in 3 weeks. Or if you start manufacturing them now, it'll take 3 weeks to do so. And then the other thing is the units required. So basically what this means is that each computer contains 2 disk drives and 1 motherboard. Each motherboard contains 90 DRAM chips and 2 other boards, etc. Okay. So we start with demand for the end item. In that case, that's our computer. So in each of the following, in each of weeks 6 to 11, this is how many computers we need to meet demand. In addition to knowing what our demand is in each of these weeks, we have some initial inventory. We start with 75 finished goods, and we're expecting also to get some returns back in weeks 8 and 10, 30 and 10, respectively. So basically, this is what a MRP schedule looks like. So we start with our computer. So in each of weeks 6 through 11, we have our demand. We have our scheduled returns. That's going to give us some more computers. And we have our beginning inventory. And so basically, these returns and inventory can subtract from the gross requirements to get the net requirements, which means we still need to build 145 computers for week 6, 165 for week 7, etc. All right. So then we move on to the motherboard. We have some initial inventory and some scheduled receipts or returns. And then we basically copy the net requirements from the computer down into the motherboard level. We're going to need that many motherboards for those computers. We subtract the receipts and then returns to get the net requirement for motherboards. And then since there's a 3, that's what this tau is the lead time. Since there's a 3-week lead time, we have to actually shift those back 3 periods, right? So in other words, if we're going to need 108 motherboards in week 6, we got to start making them in week 3, because that's the lead time. So this basically gives us our schedule for the motherboards. And basically, you just keep working downwards through the components list, or the components tree, if you will. So we could also go to disk drives. So disk drives, we need 2 disk drives for each computer. So we take the net requirements for computers, multiply by 2 to get the disk drives, subtract off scheduled returns, subtract off initial inventory, and get the net requirements, which we then shift back 1 week, because there's a 1-week lead time on disk drives. This is a very simple idea. It gives us schedules for all of the component parts that we're going to need on a weekly basis. And you can do the same thing. You can just take it down to the next level as well. I'm not sure I want to bother going through all of that in detail, because it's a very simple idea. All right, so if you look at how that MRP was set up, it's what's called lot for lot sizing. So every week we make what we need that week. And then at the end of that week, there should be no inventory left over, right? So if you actually filled out these bottom rows here of how much inventory is left over at the end of the week, it's going to always be 0, right? Because we make exactly what we need each week. Okay, so this assumed lot for lot, making exactly what we need every week and holding no inventory is not always the best solution. We actually discussed this before, right? So the next problem we're going to look at is what's called lot sizing. And basically, it's answering the question, should you aggregate some of these lots together? Instead of making exactly what we need every week, should we make more, make enough the last 3 weeks, and then we don't have to make any in weeks 2 and 3. Basically, this is going to be a trade-off between holding costs and setup costs. When you manufacture something, typically every time you make a production run, there's a setup cost involved in getting ready to make that production run. Of course, if you make enough inventory to last you several weeks, then there's an inventory holding cost associated with that. So in these lot sizing problems, we're trading off the setup cost versus that holding cost. I mentioned earlier that these MRP systems have evolved in modern day into these enterprise resource planning systems, or ERP systems. Basically, they started with MRP, and then they extended it to cover planning for staffing, for payroll, for accounting, purchasing, sales, all kinds of things are all in this ERP system, which does a lot of the planning for the entire company. So MRP, what it's designed to do is produce the main production schedules. And it turns out, at least in manufacturing, if you know what your production schedule is, that pretty much determines what's going to happen in the country. I mean, in the company. The production schedule drives most company activities. If you know the production schedule, you know how many workers you need to hire, you know what raw materials you need, and you need to order, and pretty much it keeps going from there. So basically, the production schedule determines everything that's going on in the company. And that is one of the reasons why scheduling is actually my absolute favorite topic in the world, because it turns out to be really important. Another reason I like scheduling is because oftentimes you can make things more efficient, or you can reduce costs simply by the way you schedule activities. In other words, there's good schedules and there's bad schedules. There's efficient schedules and there's inefficient schedules. But a lot of people don't know that. In fact, if you ask most people how good is their scheduling, they say it's fine. I follow my schedule every week, no problem. They actually have no idea if it's an efficient schedule or not. So that's why I find this interesting. All right, so let's move on and talk about optimal lot sizing, all right? So suppose these are the number of units we need in each of 5 weeks. It doesn't mean we have to produce exactly 210 in the first week and 350 in the second week. For example, we could decide to produce 800 in week 1, 303 in week 3, 492 in week 4, and produce 0 in weeks 2 and 5. Right? Now, every time we produce, we have a setup cost. In this example, the setup cost is $50. And if we make enough to last more than one period, we will have inventory that's held over to the next week and to the next week. And there'll be some cost associated with that inventory holding. All right, so optimal lot sizing is, should we make it every week? Should we only make one huge lot at the beginning? Should we make it every so often? What's the optimal way to do that? All right, okay. So again, each time we produce, there's a setup cost. Every time we hold inventory over, there's inventory holding cost. So what we're going to do is we're going to draw a network that represents all the possible, I shouldn't say optimal decisions, I should say all the possible decisions. So if we have an n period long problem, then we're going to start with n plus 1 nodes. And the arcs connecting nodes denote which lots will be ordered together. So I have to see a picture of it. All right, so suppose we have a 4-period problem. Then we're going to need 5 nodes. And then we say, okay, let's start at time 1, right? At time 1, one of the choices you could make is to produce exactly what is required in period 1. So R1, that stands for the number of units required in period 1. And the cost of doing that is going to be K, that's our setup cost. So K is the setup cost, R is the demand in period I. Here we're not going to worry about production costs. We're only going to worry about setup and holding costs. We're implicitly assuming that production cost is the same every period. And since it's the same every period, you know, we're going to incur it sooner or later, and it won't change the decision. If the production costs were different in different periods, however, we could still solve the problem this way. It would just be a little bit more complicated. All right, so one thing we can do in period 1 is just make enough for that period. And then we'll end up in period 2, and we will have spent our setup cost. Now, the second thing we can do is make enough for the first 2 periods, all right? So in this case, the amount we would produce is R1 plus R2, enough for the first 2 periods. And the cost of that would be 1 setup cost, plus we'd have to hold over in inventory the amount for the next period, and that would cost us H dollars per unit. So the cost, this arc here, cost is K plus H times R. It's another thing we could do at period 1, or we could make enough for the first 1, 2, 3 periods. 1 setup cost, 1 month holding for R2, and 2 months holding for R3, the amount we need in the 3rd period. Or we could make enough for the whole, all 4 periods. We'd have to hold this for 1 period, hold this much for 2 periods, and hold this much for 3 periods, and we have 1 setup cost, right? So those are all the possible things we could do in period 1. If we find ourselves in period 2, similarly, those are the things we could do. And in period 3, we could do that, and in period 4, we could do that. Right? So this is a network that represents our optimal lot sizing problem. And what's the goal? The goal is to find the shortest or least cost path from node 1 to node 5. That's what we want to find. Once we find that path, that's the lowest cost, that will be the optimal solution. So this is a very well-known problem. It's called the shortest path problem. It arises here in optimal lot sizing. It arises in many, many, many other applications. One obvious one is, you know, how does Google Maps decide, you know, when you ask it for directions to get from A to B, how does it decide what's the best path? Right? So the shortest path problem in a directed network is a problem with many uses. This is a more general representation. This is a general arc in a directed acyclic network. So basically that means that there's no cycles. You can't go around, the arcs go in one direction. That's what it means by a directed network. And there's no cycles where you can go follow arcs in the direction they're aiming and go in a cycle. So we want to find the shortest path from the red node on the left to the red node on the right. How do we find the shortest path? Well, you could enumerate all possible paths, but even in this small graph, there's a fair number of them. In a real world size graph, there'd be a lot of them. So the answer is we're going to use what's called dynamic programming backward recursion. So this is the this is sort of the methodology we're learning today. So we start with this network. We go backwards. So we start at the end node, right? So the end node, that's where we're at our destination. And what we're going to do is go backwards using dynamic programming. So the way dynamic programming works is you find a node for whom all successors are already labeled. Notice that this end node should be labeled 0, right? Because that's the destination. So this node here, all of the nodes that come after it are already labeled. This one's labeled 0. So we can label this node, right? And what we label it with is the cost of the arc plus the cost of the successor, right? So what this means is, I'm getting ahead of myself. All right, so once we've labeled this node here, then we say, are there any other nodes, all of whose successors have been labeled? And the answer is yes, this node. This successor has been labeled 0, this successor has been labeled 7. So now I can label this one. And what we do is we figure out the cost to go, the cheapest cost to go from this node to the end. So there's two possibilities. We could go here, and then from and here, right? So, or more simply, we could go here, and then we already know how much it costs to go from this node to the end. So if we go this path, it's 2 plus 7, it's going to cost us 9. Whereas if we just take this simple one, it's going to only cost us 5. So we take the minimum of those two, and we label this node 5. Then we say, are there any other nodes whose successors are all labeled? And the answer would be, of course, this one here. So next we're going to label that one. All right, so we got to find the best path. So one path is going this way, that costs 8. The other one is to go this way, which costs us 1 plus 5. Notice we don't have to go from 5 all the way in. We already know how much that costs, right? So you do 1 plus 5 compared to 8. 1 plus 5 is less. And so we label this node 6. And note that the, oops, got ahead of myself. The numbers we're putting on these nodes are typically called the cost to go. And that's simply because that's the cost that it takes to go from this node to the final node, right? We have a path, boom, boom, cost us 6. So that's called the cost to go in dynamic programming. All right, now what else can we label? We can label this node. All its successors are labeled. So that costs us, there's only one path, 3 plus 7 is 10. Now we can label this node. Notice that there are 3 possibilities, 2 plus 6, 3 plus 5, or 4 plus 10. 4 plus 10 is out. This is actually a tie here. These two paths will give us equal distance, and the cost to go from here to the end is going to be 8. Right? So this is the minimum of 2 plus 6, 3 plus 5, 4 plus 10. Now we simply keep going. Label this node, label this node. And finally, we get all the way to the end. What's the cheapest going to be? See a 15, a 14, and a 22. It's going to be 14. And we have the shortest path. And we know that the cost is 14 to get from the left to the right. Okay, so we use what's called backward recursion to solve this. That's the kind of the key to dynamic programming. And if you had a really big network, you would see very quickly that backward recursion is very efficient compared to if you had to enumerate every possible arc, all right? So it's very efficient. So now we can get back to our lot sizing problem. What do we have here? Okay, this is just what it would cost us if we made exactly what we needed each period. That's called lot for lot sizing. It cost us 4 setups. These are other, okay. So I'm trying to get, so what we're going to do is we're going to use dynamic programming to solve this. In fact, this algorithm for lot sizing was invented by Wagner-Witten. It's one of the earliest algorithms developed in operations research. And we're going to, again, like I said, we're going to use backward recursion. We've already sort of showed how that works to solve this problem. Start at the end node, we work backwards, we find the best path from the current node to the end. And basically, we're going to be finding the minimum, just like we did in that shortest path problem example. We're going to find the minimum of the paths, and we're going to label the node, and we're going to keep going backwards. All right, so let me just, okay, so you're going to use this problem. It is a 1, 2, 3, 4, 5, 6 period problem. We're going to assume the setup cost is $1,200 and the holding cost is $3 per unit per period. And then in the red box here, these are the number of units required in each period. So we start in the final node, has a cost of 0. We work backwards to node 6, and there's only one option from node 6, right? And that is to make all the units we need and get charged the setup cost. Okay, come on. All right, so now we go backwards again to node 5. And our two choices are to just go to node 6. We'd have to do a setup cost to produce the 65 that we needed in this period, plus the cost that we've labeled node 6 with, which is this 1,200 here. So one option is 1,200 plus 1,200 is 1,400. The other option is to make enough for the last two periods. That would be a setup cost, a single setup of 1,200 plus $3 times the 300 units we have to hold over between nodes 6 and 7, the last period. Now, 2,100 is less than 2,400. So from node 5, we would pick this option, and the cost to go from node 5 would be 2,100. All right, that's just the calculation. Find the minimum of the two. And so now our graph looks like this. We took the cheaper of the two options. And now we go to back one node to node 4. There's three things, three paths to consider. We could go straight to 5 and then on from there. We could go over to 6 and then on from 6, or we could go all the way from 4 to the end. Those are these three options up here. Of those, the cheapest is to make enough for periods 4 and 5. In other words, go from 4 to 6. And the cost for that arc is one setup, plus we'd have to hold over the 65 units for the second period. So that cost is $25.95 plus the cost, it's that cost plus the cost to go from node 6. Okay, so that turns out to be the cheapest decision. So that's the one we're going to pick. All right, we keep going backwards, right? We consider all of the possibilities from node 3, and it turns out the cheapest is to make enough for 3 periods and jump all the way to period 6 like that. That's the cheapest. Go back to the second node. Of all these options, we pick the cheapest, and the cheapest is, again, to go straight to 6. Finally, we go back to the first node, consider all of the options, pick the cheapest. The cheapest, in this case, turns out to be that you make enough for the first 2 periods, and now we can see what the optimal solution is, right? 1 to 3, 3 to 6, 6 to 7. You add up the costs, and that gives you the cheapest solution. So it's backward recursion, finding the shortest path in a network by labeling the nodes as you go. Okay, and that's the total cost. Okay, so that's the Wagner-Witten algorithm. It's an example of dynamic programming. It's guaranteed to find the optimal solution for a finite horizon problem, and it's very efficient. Okay, so now I'm going to talk a little bit more about sequential decision-making under uncertainty and stochastic dynamic programming. So sequential decision-making under uncertainty is kind of the ultimate in decision-making, because that's what the hardest problems are, and that's what real world problems are. Oftentimes you have to plan ahead. You can't just plan for tomorrow, but you have to plan out into the future, right? So you're making decisions as you go out into the future with randomness, with uncertainty involved. So a lot of times you can kind of view a problem. This is a very simple view. Basically, you can just make more arcs and make it more realistic. So the idea of this graph, what this graph is trying to show, is that in these blue nodes, this is where you have to make a decision, right? You have to make a decision today. And we're going to keep it very simple that you have only two choices, all right? This choice or this choice. Okay, so once you make a choice, then you observe what happens, right? And what happens is uncertain. So these red arcs represent, they're called chance arcs, or they represent the possible outcomes of whatever random variable is affecting us. For example, these two decision arcs could be we should make 100 units or we should make 200 units, and then these red arcs represent the different possible demand outcomes you could have. And then once you observe what happened in the random world to the random variable, then you come to the next period where you have to again make decisions, where you again have to make a decision in these blue nodes next period. And then you can keep going on from there, as many periods ahead as you like. But basically it's based on the idea you make a decision and then some random outcomes are observed, and then you make more decisions and more random outcomes are observed. And like I said, you can go out in the future as far as you want. What we're looking for is a policy that tells us what we should do in each state we may end up in. We're going to view this as a maximizing value. So each node, each state, each of these blue nodes we can find ourselves in is associated with some value. And the policy will tell us in any of the nodes we may end up in, what decision should we make, right? So here this says in this node, we should go up, not down. We could end up in any of these three nodes, and in either of these three cases, it tells us what we should do there as well. That would be a policy. Just a real simple example. This is only like one period's worth, but you can imagine just extending this tree out into the future, right? So each of these ending states, we have 6 ending states, and they each have a certain value associated with them. And then each of these arcs has a probability associated with them. And then this node here also has a value of 30, and this has a value of 25. And we want to decide what to do here, right? So what we need to do is start at the end and work backwards and compute the expected value of taking the up decision, going to this node, or the down. All right, so what's the expected value of being at this node? Well, we have our $30 we get here, plus the expected value of what comes after, which is going to be 0.4 times 10, plus 0.3 times 15, plus 0.3 times 8. Add that all together, and this node has a value of 40.9. You do the same calculation down here. This node has a value of 36.1. So that tells us that we would prefer to make the up decision. That would be part of our policy. And that the value of this node is 40.9. So and we could keep going back into the past if there were more arcs going off to the left. We now know the value of this node, and we continue to recurse backwards, computing the values as we move backwards as we go, and deciding what decisions we should make. All right, so I mean, you can imagine here we said there's only 2 possible decisions when there may be many possible decisions. There's only 3 possible outcomes, and there may be many possible outcomes. And if we did this for, instead of 2 periods, we did it for 10 periods, you can see that this tree could get very, very large very, very quickly. That's what's known in dynamic programming as, I believe they call it, combinatorial explosion. At some point, these decision problems explode in size, making them very difficult to solve. All right, so now I got some examples to show you. These examples are more solver-like than dynamic programming-like. But they're more production planning problems, and they're kind of like game relevant, perhaps. So in this very simple production planning model, we need to figure out how much finished goods to produce each period, and also how many raw materials to purchase each period. So those are our two decision variables: finished goods to produce and raw material to buy. We have some basic data. We have our sales forecast, so we need to make that many units at least. We could make more if we wanted to and carry them over. And we have raw material prices in each period, right? We have an initial inventory at the beginning of the problem of 100 finished goods, 100 raw materials and 500 finished goods. All right, so the costs involved are the cost to buy the raw materials, raw material holding cost, and the finished goods holding cost, which have 10 cents per unit for raw material holding, 30 cents for finished goods. All right, so basically you add up those three components of cost to get a total cost, and then you have a solver model that you can solve. Oh, before I do that, so here are the constraints that are in the model, okay? The available raw materials has to be greater than or equal to the production amount, or in other words, you can't produce more than you have raw materials for. There's an upper limit, capacity limit on production of 5,000. Production cannot be negative, raw materials purchase cannot be negative. And basically the inventory at the end of the period is required to be greater than or equal to 0. The inventory of finished goods and raw materials. That's equivalent to saying that we're not going to allow back orders, right? That's not allowed. You have to meet your demand. Okay, so the solver model is pretty simple. It's just what I said. It is a nice linear model. So we can use simplex LP. It solves very quickly and tells us what to do. So you notice that we're producing finished goods every period, and we're producing exactly what we need. Why did that change? But we are buying raw material ahead in some cases and storing it. Okay, so that's a fairly simple model. Just like in the example we used for Wagner-Witten, here we're assuming the production cost is the same every period. And therefore we were able to ignore it because you have to pay it no matter what. However, what if production cost is not the same every period? So basically I just took that same basic model and I added to it that now the production cost is going to actually increase each period. All right, so production cost is not the same. So now in addition to raw material cost, raw material holding cost, finished goods holding cost, we also have production cost. All right. Other than that, it's pretty much the same model. I just to get my production cost, I multiply the cost per unit times the number of units produced, and I add up all the costs. So again, other than that, the model is exactly the same, and it's linear, solves very easily. And now we see that we are not producing every period. There's some periods we produce 0 in, and presumably that's to avoid the higher production costs towards the end of the periods. Another thing we could try is we could try having back order cost in there. All right, so I basically took that same model. I actually took the first model we looked at, and I put in here the possibility of having back orders. So now there's a back order cost. So for each back order that we carry over to the next period, it costs us 55 cents. So that's, think of that as a cost of negative inventory if you wish. So what we have to do here in order to compute how much finished goods inventory we have at the end of the period or how many back orders we have at the end of the period, we're going to need a max, right? We need a max of 0 or some number, right? In particular, it's going to be the goods available this period minus the minus the demand, right? So if demand exceeds finished goods available, we'll have back orders. If vice versa, demand is less than finished goods available, we'll have inventory. That's what this max operator does here and here in computing back orders and the finished goods inventory. Now, the problem is that these max functions make this a nonlinear problem. So when I go to solve it, I have to use the GRG, well, I could use evolutionary GRG nonlinear. And it turns out, I was really surprised. This turns out to be a very difficult problem. I tried GRG with multi-start. I tried evolutionary. I let them both run for half an hour. And after doing that and monkeying around with this quite a bit, I was able to find this solution here. But it took a lot of effort to find this solution, I will say. Now, I also think that a smart person could probably, if you remember the homework that was due last week, there was like a regression problem where you're trying to minimize the absolute value of the residual. And there was a nonlinear formulation and then there was a special linear formulation that you had to work out. I have a sneaking suspicion we could pull a trick like that here and turn this into a linear problem. But as it stands right now, I have a nonlinear formulation that turned out to be very difficult for the solver to solve. And one last example of what we can do is now I'm going to add setup costs in, right? So every time I decide to produce in a period, it costs me 3,000 bucks. So now what I need is another decision variable, which is a 1 if I'm going to produce in this period and a 0 if I'm not going to produce in this period. Right? And then I can multiply that by 5,000 to get the production capacity. So if I decide to produce, then I can make up to 5,000. But if I decide not to produce, then I can't make anything. So basically, I now have a binary variable added into the model. I got rid of the back orders because that would make it nonlinear and integer, which would be impossible. But now I've added the setup cost in as well. And this one, even though it's an integer programming problem, it solves pretty quickly. So we end up producing in all but 3 of the periods. All right, so those are the examples. Give me a second here. Okay, so here's the assignment. The first problem is like the Wagner-Witten lot sizing problem. You're going to use dynamic program backward recursion to solve it. And this is going to be something you're going to do by hand. Basically, you're doing backwards recursion. This is a problem similar to the first example.
Are you sharing your screen, Professor Stern?
I'm not sharing my screen. I'm surprised no one mentioned that to me. Okay, here's the first problem. It's basically, you're going to use Wagner-Witten. It's a little bit more complicated because the setup costs and the holding costs vary each period. The second problem is very similar to the first example problem. Third problem says add in setup costs. That's going to be like the last example I covered, but did not include in the examples I posted online. The third is one of these stochastic decision-making problems where you will find the optimal policy given these costs and probabilities. And these problems are all different than they have been in the past. Why is that, you might ask? Because it has become blatantly obvious that people have been passing down solutions from year to year. So all of these problems are different and indeed harder. Why are they harder? Because I'm pissed that people are using answers that they got from other people. Here's a whole new, brand new problem for you involving golf strategy, which again, you're going to use backward recursion to figure out the solution for. All right, so brand new problems for everybody. That's all I got for today. Does anybody have any questions? I was really, really disappointed to hear that Sachil tell me that people are using solutions from they got elsewhere. I expect more out of IBE students. I really do.